AP Calculus BC, Unit 5, Day 11, Office Hours. These are the answers at the top to the multiple choice questions. I will be going over the work involved. Pause the video if you need to check these. All right, let's do this. So, first one just says, in decomposing by the method of partial fractions, one of the fractions is what? So we just got to decompose this. So the way we do that is we split it up. We're not going to actually do any calculus on this one. And we do a over x minus 7 plus b over x plus 4 multiplied through by the least common denominator. Use the heaviside approach to get rid of. We could plug a 7 in here. Be 35, that'd be 33 equals 11a. So a equals 3. And we can plug in a negative 4. And we get negative 22 equals negative 11b. So b equals 2. And so this is going to be 3 over x minus 7 plus 2 over x plus 4. And we're hoping one of those is in our list. So that will be C. Okay, next one. Next one we're actually going to integrate. So can we, you know what? I think we just use regular U-Substitution. Don't make these harder than they have to be. U equals the denominator, 2x. This is not inverse trig. Don't want the 2. X dx, perfect. So it's going to be 1 over 2 du over u equals 1/2 natural log of the absolute value of u. Need to change it back in terms of the original variable. Absolute value of x squared plus 1, which is absolute values are unnecessary because it's going to be positive no matter what. I'm going to plug limits back in. 1/2 natural log of 10 minus 1/2 natural log of 2, which isn't on this list, no surprise. We could use log rules to combine these guys together and get that, and there's that answer right there. So we got to be able to work with, I mean, sure, this was an answer, but we had to work with log rules to get it to look like what they have. I mean, of course, from here, you could say natural log of the square root of 5 could have been an option also. Okay, next one. We can't factor this, and so we're going to have to use partial fractions. So we're going to say a over x plus 3 plus b over x minus 3. Multiply through by the least common denominator. Okay, we could plug a negative 3 in. So a equals negative 1/6. Plug a positive 3 in. B equals positive 1/6. So this is going to be negative 1/6 integral of dx over x plus 3 plus 1/6 integral of dx over x minus 3. And that's going to give you negative 1/6 natural log of the absolute value of x plus 3 plus 1/6 natural log of the absolute value of x minus 3 plus c. I don't see this answer here. We probably got to use some log rules. I'm going to leave the 1/6 out because they both have it. This is going to be on top. X minus 3, x plus 3 is going to be on the bottom, plus c. Maybe we have more luck with that answer. Looks like D. So you got to be able to manipulate your answers. Okay, number 4, for what value of k greater than 0, does this value equal this? Well, I think we have to kind of actually try and integrate this. Now, k is just a number, so the antiderivative would be 4k x squared over 2 minus 5kx. And then we could plug limit in and be 2k cubed minus 5k squared minus 0 minus 0. And then I think we want to solve this. So we want to bring everything to one side. 2k cubed minus 6k squared equals 0. 2k squared out. K minus 3. K equals 0. K equals 3. It says that k has to be greater than 0, so this is the one we're going to go with. K equals 3. All right. You should be able to do these problems in 2 minutes or less. Multiple choice. Average. So this is good practice. Okay, number 5 says if the function r equals f theta is continuous, non-negative, then the area enclosed in the polar curve for this function would be what? So I mean, we can just, there's a lot of general stuff here. So you have a curve and it goes from like theta equals alpha to theta equals beta, and you want to find all this area, right? Essentially, that's what we're trying to do. So the formula is 1/2 r squared d theta, and we're going from alpha to beta. And in this case, they said that r equals f theta. And we just got to pick the right one. This one has the squared in the wrong spot. This one doesn't have the squared. This one has the squared in the wrong spot and an extra theta. This one doesn't have the squared. This one looks good. All right, number 6, we got to integrate this. Let's try U-substitution. I think U-substitutions work. It doesn't always have to be crazy. It can be old techniques. This looks perfect. Okay, x dx. So this is going to be 1/2 square root of u du, which I'm going to make it u to the 1/2. This is going to be u to the 3/2 divided by the new exponent, multiplied by the reciprocal. I'm going to change it back to its original variables. So let's see, is this on there? 1/3 x squared plus 1 to 3/2 plus c. Perfect. All right. Number 7, U-substitution. And that's where we're going to have to use lipit. Integration by parts. Tic-tac-toe. This is poly. This is trig. So you got poly and trig. Now, the cool thing about that is you can use a shortcut, right? So you should, the thing that if you keep taking derivative goes 0, that's the thing you want to do that. And the other one we're going to integrate. So it's going to be negative cosine x, and it's going to be negative sine x. And the first one's positive, next one's negative, alternates. And we multiply through by a diagonal. And so we get negative x cosine x plus sine x plus c. Negative x cosine x plus sine x plus c. You could do it the long way, which you should be able to do. This one wouldn't be that bad. It wouldn't be a repeated one. This is repeated ones that this shortcut becomes just super helpful, but this is still a lot faster than doing it the regular way. Number 8 is, so we're trying to just integrate this, but not all the way. So I think we got to do partial fractions. So this is going to equal a over x plus b over x plus 4. So we're going to multiply through by the least common denominator. Plug a 0 in if you want. A equals 1/4. Plug a negative 4 in. B equals negative 1/4. So this is going to be 1/4 dx over x minus 1/4 dx over x plus 4. This is how I would write it, but we're at the mercy of multiple choice. Do we see anything like that? Well, the 4 could be in here. So this one's close, but That's the thing that's wrong there. This is the right one. It needs to be a minus. All right, number 9. I think we got to do lipid, integration by parts. So we have poly expo. So we can use a shortcut. So I'm going to rewrite this. Shortcut, keep taking derivative till 0, integrate the other side, positive, negative, positive, multiply it diagonal. So we're going to get x e to the x minus e to the x. And this is a definite integral, so we still got to plug limits in. 2e x squared minus e squared. If you plug 0 in, you get 0 times e to the 0, which is 1, minus e to the 0, which is 1. So it doesn't all disappear. It's going to be 2. It's going to be 1e squared plus 1. E squared plus 1. E squared plus 1. There we go. Number 10, I think regular U-substitution might work. Don't make it harder than it has to be. 2x dx, perfect. I don't want the 2. X dx. It's going to be 1/2 du over the square root of u, which I'm going to rewrite as 1/2 u to the negative 1/2 du. So that's going to be u to the positive 1/2 multiplied by the reciprocal plus c. You need to change it back to its original variables, and this is a definite interval, so we still got to plug the limits in. So this is going to be square root of 25 minus square root of 16. It's going to be 5 minus 4 is 1. Won't work out simple. All right, next one. Ooh, I think we're going to have to do inverse sine, but this needs to be a 1. So we're going to take square root of 4 out, which is a 2. And so that's going to be 1 minus x squared over 4. So I factored the square root of 4 out. So this is going to be where my u goes. What do I square to get x squared over 4? It's going to be x over 2. So u equals x over 2. Du equals 1/2 dx. And I want the 1/2. I'll rewrite it. I have a 1/2 already. Then I'm going to get another 2. And it's going to be du over the square root of 1 minus u squared. So that's going to be inverse sine of u. But then we need to change it to the original variable is x over 2. So I'm looking for now, arc sine is the same thing, by the way. Arc sine is the same thing as inverse sine. So I think this is going to be it right there. If you want, you could do trig substitution on this one, possibly even number 10. I wouldn't, but you know, it's out there. If you want to try to do it a little more challenging approach. All right. Okay, number 12. I think we're going to do partial fractions here. 2x, x, 1, 1, positive, positive. So this is going to have to be a over 2x plus 1 plus b over x plus 1 dx. So I'm going to multiply through by the least common denominator and get 1 equals a, x plus 1 plus b, 2x plus 1. Plug a negative 1/2 in to make the b go away. And I get a equals 2. Plug a negative 1 in to make the a go away. And I get b equals negative 1. So I'm going to rewrite this. 2 integral dx over 2x plus 1 minus 1 integral dx over x plus 1. So there's going to be 2 natural log, the absolute value of 2x plus 1. Be careful though, an extra 2 is going to pop out that we didn't want. Chain rule, Got to divide by 2. Watch out for that. Now, all these answers look like they took advantage of the log rule, so we are going to do that. 2x plus 1 over x plus 1, all inside 1, absolute values. So we see that right there, answer D. Okay, number 13, probably partial fractions, right? Plus 2 plus 3. So we're going to do that first. A over x plus 2, b over x plus 3 dx. Multiply 3 by the least common denominator. Plug in negative 2. A equals 1. Plug in a negative 3. B equals negative 1. Rewrite it. Dx over x plus 2 minus dx over x plus 3. Natural log the absolute value of x plus 2 minus natural log the absolute value of x plus 3 plus c. Probably use log rules. Now this is a definite integral, so we're going negative 1 to 1, so we could have kept writing that. So natural log of x plus 2 over x plus 3, negative 1 to 1. So natural log of 3/4 minus natural log of 1/2. I don't see that answer on there, so we probably got to use log rules. This is natural log of 3/4 divided by 1/2. Natural log of 3/4 times 2 over 1, which would be natural log of 3/2. Natural log of 3/2. Answer A. Just got to go with it. All right, 14. Could we do U-substitution? I mean, I don't know if we really have to. This is an exponential. So what's the antiderivative of exponential? It's itself divided by the natural log of the base. But also this 3 is going to pop out, so we need an extra 1/3 plus c. So I think that's the answer we're looking for. 2 to the 3x over 3 natural log of 2 plus c. So nothing really fancy here. I didn't even end up using U-substitution because it's just extra constant that pops out. But I think answer B is what we want. So that's just the answer derivative exponential. It's a derivative of an exponential backwards. It doesn't have base e, so it's kind of special. Okay, 15. We could try U-substitution just to make this simpler. Seems like it'll work. I don't think we'll have to do anything else more complicated. So this is going to be negative du over the cube root of u, which I'm going to rewrite as negative u to the negative 1/3 du. So that's going to be negative. I'm going to use power rule, add 1, divide by the new exponent, plus c. We need to rewrite it back in terms of its original variables, 8 minus x to the 2/3. And this is a definite integral, so we're going to actually plug the limits in. So negative 3/2, if you plug 8 in, you get 0 to the 2/3, minus negative 3/2. Plug in 0, you get 8 to the 2/3. That goes away. That becomes positive now. I do the cube root of 8 first is 2, squared is 4. So that's the same thing as 4. So the final answer is going to be 6. But I just forgot something. This is actually an improper integral. Something we got to watch out for because x cannot equal 8. Get division by 0. So the proper way is to take the limit as b approaches 8 from the left-hand side because we're going 0 to 8, so we're approaching 0, of and then you put a b there, so it'd be negative 3/2 8 minus b to the 2/3 minus negative 3/2 8 to the 2/3. So we would do it, it'd be similar work, but here when you plug this in, it's going to 0, and it's going to be a very small negative thing, but it's going to go to 0. And so you're going to end up getting this, which is 6. So the technical way of showing the work, which I guess isn't as important on multiple choice, is to write it as a limit. Okay, so let's see, 16 says if the substitution is made, then what do you get? But here's a key thing: you got to make sure you change the limits. These are x limits. You got to change them u limits. It's really simple to do, but it's easy to forget to do, and I guarantee they're going to take advantage of it here. So they're telling you right now that that's what u is. So du equals 2x dx. Probably don't want the 2. Now this one's a little more complicated because you get 1/2, and you're still going to have an x squared on the top left over. So how do we deal with that? And that's something we've done before. We could say, well, if u equals x squared plus 1, then x squared equals u minus 1. We could plug that in for the x squared and still pull it off. So that's going to be u minus 1 over u du. Now to integrate this, we want to distribute that division. All right, so then we get 1/2 u minus the natural log of the absolute value of u. Oh, shoot, we're not even supposed to go that far. So it looks like this is good enough, but we do need to change the limit. So u here, you plug in x equals 0 into that, and you get u equals 1. The top one, you plug x equals 2 in. 4 minus 1 is 3. So we need the one that has limits 1, or let's see, 5. 1 to 5. 1 to 5 of u minus 1 over u. u minus 1 over u. And there's a 2. I think it's that one. This one has the wrong limits. Otherwise it looks good. This one has the right limits, but this is supposed to be a minus. And these other ones just aren't right. 17 is found by using which of the limits below. So they're essentially, I think they're asking you to rewrite this as an improper integral, right? The technical way. So a t cannot equal -1 or t cannot equal 4. And so 4 is the issue. That's okay. So we've got to approach 4 from the left-hand side. So when we're not even asked to change this to partial fractions, we're going to say limit as b goes to 4 from the left-hand side of t minus 2, t plus 1, t minus 4, dt, and it's going to be 1 to b. So something like that, I think, is what we're looking for. Now, they have x's instead of b, which is fine because we have t's inside, so it's a different variable. But this is the key thing. We're trying to approach 4 from the left-hand side because it's improper. And it needs to be up here on top. See, this one's wrong because of that. This one's just going to the wrong thing. Those are all going to the wrong thing. So we're just trying to rewrite it. 18, I don't think we can, it says, so they're giving us the antiderivative, but we're trying to find f of x, I guess. I feel like this is probably going to be integration by parts. I think this is going to be lipid. So this is poly trig. So I think we can use this shortcut. So derivative is 1, 0. Antiderivative of secant squared is tangent. Antiderivative tangent, though. Oh my gosh. So I think we can use a shortcut, but what's the antiderivative tangent? You have to use like usubstitution. U equals cosine x, du equals negative sine x, dx. Don't want the negative. So that's going to be negative du over u. So that's going to give you negative natural log of the absolute value of u. So this is going to be negative natural log of the absolute value of cosine x. Plus, minus, plus, multiply through by the diagonals. So we're going to get x tangent x, and this is going to be plus natural log of the absolute value of cosine x plus c. We're specifically trying to find this, so that's this right here, x tangent x. Now we could also do this without the shortcut, and I'll go and show that just as a quick reminder of how to even do it. So let's see, where are we? So without the shortcut, we'd say polytrig. We'd say polytrig. So the first one on the list is your u, so x, and the other one is your v prime. So secant squared dx. And so then we find u prime equals 1 dx and v equals tangent x. We integrate that. And then we write, okay, it's going to be uv x tangent x minus the integral of the two new things, which is tangent x dx. We're going to have to think of it as sine x over cosine x. Do u substitution, u equals cosine x, d equals negative sine x, dx, don't want the negative, right? So this is going to be negative negative 1 over u du plus plus. So that's going to be natural log of the absolute value of u plus c. You write it back in terms of the original variables, natural log of the absolute value of cosine x plus c. And so we get the same thing. So that's how you do it without the shortcut. The shortcut's a little quicker for sure. Okay, next one. If we're going to integrate natural log x, it's not 1 over x. It's going the wrong way. So this is one where we need integration by parts limit. And we have to get extra creative. Think of a 1 in front, which is going to be a polynomial of degree 0, and then a log. So we have polynomial log. Can't do the shortcut. So u equals the log, natural log of x, v prime equals the 1 dx, and we do u prime. It's going to be 1 over x, and v equals x. So we do uv, x natural log of x, minus the integral of the two new things, 1 over x times x dx, which is just 1. So we get x, natural log of x, minus x. This is a definite integral, so we don't put the plus c. We're going to evaluate it, plug in limits, 2 natural log of 2, minus 2, minus 0 natural log of 0. Ooh, that just gave me an idea that this is actually an improper integral because x cannot equal 0. So technically, we should be taking the limit as b approaches 0 from the right side. Definitely not the left. Natural log is not even defined on the left, but on the right side of 2 natural log of 2 minus 2 minus b natural log of b minus b. So this is going to 0. As we approach this, this is going to negative infinity, and this is going to 0. So technically, this is an indeterminate form. You can't say it's 0. It's something tiny times something big. It could end up being super big or super tiny or something in between. So this is L'Hopital's rule, is the indeterminate form. So if you remember from a couple chapters ago, we rewrite it. So it's natural log b over 1 over b. And that gives you negative infinity over positive infinity. So we definitely supposed to get, so now we can do L'Hopital's rule. So the top's going to be 1 over b. The bottom is negative 1 over b squared. And then we could simplify it. And that's going to be negative b. And so it's going to go to 0. So eventually I prove that this is going to 0. 0, that's not for sure 0. This is for sure 0. So our final answer is 2 natural log of 2 minus 2. 2 natural log of 2 minus 2 is b. Now undefined or infinity could have been a possible another situation, but this is how you would have done it. This is the work you would show for this indeterminate form right here. L'Hopital's rule. Okay. Number 20, one of our famous 3-part Roman numeral multiple choice problems. Just like 3 problems in one. Which of the following improper intervals converges? So gives you a nice answer. It doesn't go to infinity. So this one would be, I'm going to get lazy here because it's a multiple choice. I'm not going to do all the limit stuff. So I'm not going to do it the most proper way. So the antiderivative is negative e to the negative x. I'm just going to put infinity here. Then I'm going to say, okay, well, this is negative 1 over e to the infinity minus 1 over e to the 0, which is 1. That goes to 0. This goes to 1. So that one converges. This one right here is, the issue is this right here. So if I'm going to be lazy, I'm going to show a little bit more. So we're going to go, we got to approach 0 from the right side. So if anything, this is a lazy approach, but at least it shows you that's a one-sided limit. And so when we get negative 1 over 1 minus negative 1 over 0 plus, which means this is going to blow up. This is going to go to positive infinity. So this one diverges. So that one's out. This one's in. This is x to the negative 1/2. 0 is the issue, so we're going to approach 0 from the right side, one side limit. Antiderivative. So this one converges, so that's good. So we're going to say 1 and 3. 1 and 3. Okay, I gotta show you work though. I don't see how you're figuring that out without showing you work. Okay, this one we're going to infinity. Also, x cannot equal 0 because this is the same thing as 1 over x to the 5/4. So that's division by 0. 0 is okay though because it's not between our limits. So I'm going to go ahead and be lazy and not do all the limit stuff. So it's going to be x to the negative 1/4 divided by the new exponent. And I'm just going to write infinity here. I'm going to rewrite this as negative 4 over the 4th root of x. So negative 4 over the 4th root of infinity minus negative 4 over the 4th root of 1 plus. That's going to go to 0. Our answer is going to be 4. Last one, this absolute value. You could kind of like write it as like a piecewise function. I would probably just split it up. I'd probably say, okay, you know what? I'm going to do negative infinity to 0. And that means that x is going to be negative for sure, which is going to force it to become positive. So that's going to be the opposite of it, right? To force it to become positive. And then I'm going to do 0 to positive infinity. And that means x is going to be positive, so we can just drop the absolute values. And then that's what, usually the way we deal with absolute values is we split them up into their different cases. So this one, again, I'm being lazy. It's going to be e to the x. and I'm going to go negative infinity to 0. And there aren't any infinite discontinuities here. This is going to be negative e to the negative x, 0 to infinity. So it's going to be e to the 0 minus 1 over e to the infinity because it's negative, plus this is going to be negative 1 over e to the infinity because there's a negative there, minus negative 1 over e to the 0, plus. This is going to 1. This is going to 0. This is going to 0. And this is going to 1. So we have 1 plus 1 is 2. So, I mean, that's the way I would do it. I'd split it into its two cases and then integrate each one. Figure out how to get rid of the absolute values for the negative case. The way you get rid of the absolute values, if you know the inside is a negative, is adding an extra negative to it. If the inside is going to be positive, you can just drop them. There was already an extra negative right here that ends up, in what you get after that. So this is the work I show. This is the lazy work. This is the laziest way to show this. All right, that's it. Good practice.